Hello everyone, welcome to another section of the measure theoretic probability. So today on lecture 11 we will be talking about the second Borel-Cantelli lemma, second BC. We talk about the first BC in our lecture 10. Alright, so there is something you have to note when it comes to the second BC. That's very key in it when you are stating it. We need the events to be independent, but for the first BC we don't need the events to be independent. So the events need to be independent for the proof to actually hold. Okay, so let's go. If we have a sequence of events an, which are independent events, and the sum of their individual probability equals to infinity, then the probability of the lim sup of an equal to 1. So how do we prove this? So we know that the probability of the lim sup of an is equal to the probability of the intersection union of what? Of ak. And now the probability of the intersection of the union of ak is equal to 1 minus the probability of the union intersection of ak complement. Here you take complement of it. We know that the probability of a is equal to 1 minus probability of a complement, or probability of a complement is equal to 1 minus probability of a. So that's what we just did. So it suffices by countable subadditivity to prove that the probability of the intersection of ak goes towards 0 as n goes to infinity. So we need this part to go towards 0. We just need this part to go to 0, and we are done with what? With the proof. So how do we do that? Now, since the sequence are independent, then so as its complement are also what? Independent. And then by definition of independence, if you have probability of the intersection of ak's complement is equal to the product of their individual probabilities of what? AK complement, implying that we know that the probability of AK complement can be written as 1 minus probability of what? AK. Okay, all right. So using the fact that when you have 1 minus s less or equal to e to the power minus s, then we apply this fact that then the products of 1 minus probability of ak is less or equal to the product of e to the power minus what? Probability of ak. And if you product this infinitely often, then we get e to the power the sum of what? Probability of ak. We know that from above, we know that this sum goes to what? Infinity. Then we have this going to infinity, this goes to 0. Then we are done with the proof. So now we have the probability of the lim sup of an equal to what? 1. So this tells you that the independence of events are really key for this proof to hold. Let's check some example and know how to apply this. Alright, so this is an example. So we need the sum of the individual probabilities to go to infinity, then we apply the second BC. So let us assume one has a frequent and tosses are independent of each other. What is the chance of seeing a run of n equal to 100 to the power 100 hertz infinitely often? Note that since you have a frequent, then the probability of seeing a head is 1 over 2, and probability of seeing a head n times is 1 over 2 to the power n. We know n is equal to what? 100 to the power 100. And when you have 1 over 2 to the power 100 over 100, then it's approaching 0. We define this as what? Epsilon greater than what? 0. Are we good? So let S1, Sn plus 1, S2n plus 1 be the event that the run start from this position. So the sum of their individual runs, the sum of the probability of the individual runs is equal to what? The sum of I from 0 to infinity of these errors. And if you sum them together, it goes to what? Infinity. Then by the second BC, the probability of seeing the run infinitely often is equal to what? 1. So this is one of the use of the second BC. Okay, right. Now let's talk about something important as well. We call it the Kolmogorov's 0-1 law. Kolmogorov's 0-1 law. Alright, before we talk about the Kolmogorov's 0-1 law, there's something we have to note. Alright, so we talk about that one here, then talk about the Kolmogorov 0-1 law later. Let A1, A2 true to infinity be a sequence of events in the probability space. Let us consider the sigma field, that is J, equal to the intersection of the sigma field generated by an plus 1 up to infinity. This is called the tail sigma field. So the tail sigma field is the intersection of what? All these associated with the sequence an. The elements of this sigma field, that's the tail sigma field, are called what? The tail what? Events. We call them the tail events. we call them the tail events. So the tail events are only determined by a n for large N. So we ask ourselves, are the whole space and the empty set tail events? Yes, indeed. Since J is a sigma field, then we have the whole space and the empty sets being what? Tail events. Are you okay? All right. So we know what we mean by tail events. So we need tail events to be able to talk about the Kolmogorov 0-1 law. All right. Okay. So let's check it out soon. So now theorem. Kolmogorov 0-1 law. Kolmogorov 0-1 law. So note, if A1, A2 are independent, so note the Kolmogorov 1 law leaves independence of this event, are independent event, then for every A belonging to this tail sigma field, either probability of A equal to 0 or probability of A equal to 1. So here comes the Kolmogorov 0-1 law. So fact, we are going to use a fact to prove this. So if you have s squared equal to s, then it implies that s equal to 0 or s equal to 1. Since if you have s squared minus s equal to 0 implies that when you factor s out, you get s into bracket s minus 1 equal to 0, s equal to 0 or s equal to 1. So proof. Then we fix A belonging to what? The tail sigma field. We fix A belonging to what? The tail sigma field. We will show that A is independent of itself. Show that A is independent of itself. Note that by independence, if you take probability of A intersection A should be equal to what? The probability of what? A times probability of A. When you intersect A with itself, you get probability of A, implying that probability of A times probability of A equal to what? Probability of A squared. This implies that probability of A equal to 0 or probability of A equal to 1 from the fact above. From the fact above. So there are further proofs to it to show that A is independent of itself. So we end our lecture here, and thanks to everyone listening and watching it. Alright, see you later in lecture 12. Have a good day. Bye bye.